everyone. Sorry I'm a little bit late today because my working computer just crashed, so I'm switching to my personal computer. It's weird that
So fun to hang out.
always keep crashing
It's
when
fun to
I
talk to
play
Rachel.
the
I am. This
slides.
chair is very nice. I don't know. It's like Mormon people. Not that Mormons are bad. I was just like, it's just weird that he called my dog fat. I know he didn't mean it bad way.
Okay, let me share my screen. Okay, so today we'll talk about sterilization. This is the week 6 already, almost half of the quarter. So the busiest time usually, and I know guys you have a lot of the quiz, the assignment, and the lab report for this class. So keep up the great work. I think we are doing very good till now. Okay, so this lecture might last a little bit longer because it has a lot of content to cover. So sterilization, basically we will cover the conventional sterilization and what is the commercial sterilization. So the commercial sterilization is more used for the food industry now. It's like a modern food technology, but sterilization, the conventional one, is more for in the past and more for the theoretical. And we'll learn about the conventional retort and what is the aseptic processing. And we'll learn about 3 different commercialization systems, commercial sterilization systems, the batch retort, continuous retort, and aseptic processing. And we'll try to pick appropriate retort system for different food types. So in the grocery store, we can find a lot of different sterilized foods like cream milk, a lot of vegetables and meat, sausages. So it's a lot. Although the market is not growing as fast as the frozen food, because frozen food is one of the biggest trend right now. But the sterilized food is still very important part of the market. So it is a unit operation that we apply a extremely high temperature for a very long time to destroy almost all the microorganisms. Okay, especially the spores, which are very thermal resistant, and we're making sure that they are destroyed. So a little bit a comparison between them. So far, if you guys recall, we have learned blanching, right? Then we learned about the pasteurization, and finally we learned about sterilization. So pasteurization has the most mild temperature at 100, less than 100 degrees C, usually 65 or 70, more than 70. But in sterilization, we apply more than 100 degrees C of the temperature, normally 121 degrees C. And in pasteurization, we only deactivate those pathogenic microbials and enzymes. But in sterilization, we want to destroy them in a much greater way, almost everything. And the shelf life, that's why that sterilization can last for more than 6 months, but only a few days to a few weeks for pasteurization. And because the pasteurization is more mild treatment, there's less nutrient loss and better sensory quality. But in sterilization, because everything's over processed, so the quality in both sensory side and nutrient side are much worse. But on the other hand, um, we don't need to store them in the refrigerator, but for pasteurization, we usually need to refrigerate them. So that's their difference. So as we know that for sterilization, it's usually for the reason that we keep over process it, because we have a uh, uh, very dangerous bacteria, Clostridium botulinum, that can sometimes be lethal when we consume it. So we are always trying to ensure a 12D reduction of that species. But so typically to achieve the 12D process, we have to process it at 121 degrees C for more than 15 minutes. If you guys recall the lab last week, um, I put out a time chart for you that we have the 3 stages of the heating, right? There's a come up time, which is about more than 20 minutes. I don't remember the exact number, but that's the temperature brings that's the time brings the temperature from the room temperature, 22 degrees C, to 121 degrees C, which is the targeting sterilization temperature, right? And then we hold it for about 15 minutes. Normally, we hold it for 15 minutes, but in our case, we did for 23 minutes. And then afterwards, we cool it down. So the 15 minutes here or more is just for the holding time. But the entire process can take more than 1 hour, because to include those heating and the cooling time. So that's to ensure the complete kill of the bacteria by the very harsh treatment. But on the other hand, we are also over processing it. But for commercial sterilization, it's kind of different. So in this case, we are no longer seek for the 12D process. So remember, 12D is 12 decimal reduction, okay? 12, basically 12 log. So it's quite a lot. But for commercial sterilization, we are only trying to ensure that we kill all the pathogenic organisms and reduce the spoilage organisms to achieve stable shelf life, which means we still have some residual of the spoilage organisms, but they typically we consider that they don't cause any quality issue anymore, because they usually do not multiply anymore, or they are in the dominant in the dormant, basically not active. So that's how they're different. Difference between the commercial sterilization and the conventional sterilization. So there are a lot of commercially sterilized foods, and um, in those type of foods, we are trying to make sure that all tox forming and the pathogens, they are destroyed, but there are still spoilage microorganisms there, a very small amount, and they are tested. Normally, we do extended shelf life to make sure that those spoilage uh, organisms do not cause any problem within the shelf life. And they typically have more than 6 months of shelf life. So to determine the heating time for a food product, usually we have to consider several different aspects. For example, the heat resistance of the microorganism. For example, I showed to you that different microorganism they have different sensitivity to the foods, and also either the food is acid food or non-acid food, right? And you guys had the exam question, and you guys did pretty well. Acidic foods requires less treatment time, and the shape of the container matters because larger size will require longer time for the heat to penetrate. So in that case, we need longer time. And the physical state, which is usually referred as the viscosity. So the viscosity, more viscous foods will require more agitation during the processing. So because there's not much of the liquid convection in the food, you guys compare the heating curve of these four food products in the last lab, and you can see that some food heats up really quick, right? And some food like the diced tomato heats very slow, and even after the holding time is done, it only reached the 90 degrees C instead of 121. So that is the consequence of having a very viscous foods without too much agitation. Okay, you guys can always raise your hand or stop me if I talk too fast. Okay, so code point. So remember that you guys did a insert a thermocouple last week to the can to monitor the temperature during the sterilization. And actually, we used the thermocouple. The height was set to be 1/2 or 1/3 to the can, right? And that's the actually we call it thermal center or the cold point. The cold point is actually the part of food that is heated the slowest in the can. You can imagine that if we have a steam is heating up the can, there's a heat penetrating through the wall of the can. So on the side of the can, the food will heat up rapidly, but in the core will heat up very slowly. So if the heat is only transferred by the conduction, and then the thermal center is actually in the middle, in the right middle, right? But if in some cases we have the conduction, if we have the conduction, uh, if we have convection in the liquid, then in that case we will have the thermal center or cold point a little bit lower, than the middle. That's because the hot liquid usually has lower density, so they have the tendency to move up. In that case, we will have the thermal center a little bit lower than the conduction case. Is that understandable? So the 1/3 of the height is actually from the experimental measurement. There is really hard to, there's no physical meaning out of it. It's all experimental data because it's really a function of the viscosity of the food. Because assume that it is very viscous, then the thermal center will be right in the middle, right? So, but when we gradually increase the viscosity, then the movement of the liquid upon heating gets slower and slower. And then this thermal center gradually lower to the 1/3 height. Sometimes I saw in some cases even go to 1/4 of the height. Oh, I was wrong. So if it's very viscous, then it should be in the middle, right? Because there's no movement at all. But in those if we have water that moves very fast, the thermostander will go below it, because those hot liquid, when they are not viscous, they can freely move surrounding the can. So in that case, it's more um, the thermostander is a little bit lower. Does it make sense? So the more convection, the lower the thermal center. And the convection is for those freely moving liquids. Okay, so that's about the code point. It's a very important concept actually. I hope if I might not explain well here. Okay. All right. So the commercial sterilization system, there are three types. The batch system, most basic one, and we have a continuous retort system and a ultra high temperature UHT, which we learned in the pasteurization, and they usually combine with the aseptic processing system. So those three are the representative types of the commercial sterilization system. So the first one is the batch system. A basic, so this is the most basic one, the steel retort, which means um, there's not much agitation. Everything is placed there without any moving. So there are a couple ways we do agitation. One is just by shaking. The other way is to rotate it. And this one, we just sit it there and use steam to heat it up. And then after treatment, after the thermal processing, we use water to cool it down. So that's how it works. Very simple. And they have different setup, the vertical and the horizontal. Okay, I think the horizontal one has larger capacity, because the vertical one, if you make it larger, it will get higher and higher. And the rotary retort is another type of steel retort. No, it's another type of the batch retort. Basically, we place the can inside the retort, and during the process, those cans, they are rotating in a certain speed. And this rotate is pretty good for those viscous foods, because as we talked before, there are two types of heat um, transfer, conduction and convection. If we have a non-viscous liquid, the convection will be driven by the density difference, right? But when we have a very viscous foods, there's not much of the convection, because assume that imagine you have a tomato paste, and then when you heat that up, there's not much of moving of the liquid, right? But if you water, then the water can freely move. But in that case, in the case of tomato paste, we still have to induce some of the agitation. Otherwise, you see from our lab that the diced tomato doesn't heat up that quickly. So we have to artificially induce some convection. And in that case, it's not convection anymore, because the convection is spontaneously by the gravity difference. In that case, we call it more like a agitation. And in this, for the rotary retort, the agitation can be provided by the rotation. So actually, usually if we have a rotary retort, um, I would design the lab to compare the steel retort and rotary retort, so you guys will have a better idea how their heating curve are different. But we don't have a rotary retort here, so this is uh, uh, but at least you can see that the the viscous fluid doesn't heat up very well. And this is another type of retort. It's called overpressure retort. It's pretty good for those um, um, for those pouch processing, because in the overpressure retort we apply a larger amount of pressure there. For example, if we have a conventional retort, their pressure is usually 15 psig. Do you guys know what is psig and psi? This is a very confusing concept, I guess. Oh, Chris. No. Without.
Oh, I'm only aware of what PSI is, not necessarily what PSIG is.
Okay, okay. I thought you want to answer this question. So PSI stands for the pressure per square inch. The G means the gauge. So the 1 atmosphere is equal to 14.7 psi, and anything beyond that. So when we talk about the PSIG, it's really the difference between the pressure and the atmosphere pressure. So for example, if we have 15 PSIG here, it means the pressure is 15 PSI higher than the atmosphere pressure. So that's why it is equal to 29.7, because we have the basic, the base is 14.7, which is for the atmospheric pressure. Does it make sense, guys?
Could you repeat that one more time or just go
Yeah.
over that?
Let me try to write something here. So I thought this was covered in your previous class. So 1 atmosphere is equal to 14.7 psi. So this is equal to not 0 psig, because so when we talk about the psig, is the pressure difference between the current pressure and atmosphere pressure. So when we have 0, it means it's normal. But so this is equivalent to 14.7. But when we have so that's why that when we talk about the 15 psig, is actually this is equal. This means it's 15 psi greater than 15 psi greater than the atmosphere. So it's equal to 15 psi plus the atmosphere, which is 14.7 psi. So it's equal to 29.7 psi. Does it make sense?
Does that just mean that we're pretty much accounting for the overall pressure that just the atmosphere has on whatever we're measuring?
Yes. Yes, you are right. Let me try to find a figure, help you better understand. PSI and the PSIG. So that's because we in the past we don't know what is it's usually it's comparing the here we go. So when we are talking about PSI, the baseline is the zero absolute, which means the vacuum. When we talk about the PSIG, the baseline is atmosphere pressure. Does it make sense? No? And the difference between them is the atmosphere pressure, which is 14.7. Is that better? Okay, so I will. So if you are still confused, we can. You can always come to ask me in the office hour. I think this is a very important concept, and in the future you will do a lot of when you're doing something related to calculation, they will give you one number, and it really depends on the number. You have to do some like conversion. So this is very important actually. It's just a baseline difference. All right, so when we talk about the still processing, we know that the batch processing, it's not very efficient because we have to put in the sample, then take it out. But for the continuous retort processing, there's much less labor required. And in most cases, we use something called hydrostatic retort. And you can see the process looks very complicated, right? And why is there water? So let's watch a system. This is a sample system that I found very helpful from JBT. There's no sound with it actually, but it really helps us understand how the continuous system works. Let me go to the part I want to go. Okay, so as you can see, this is a continuous system, and we have can that is filling inside, and then the can will be sealed, or not sealed, but loaded on those conveyors, right? Those conveyors can fit like 5 to 6 cans every time, and then afterwards they will be fed into the system. And in the system, you can see there are different color codes. So those different color codes represent different regions, functional regions. The orange part is the come up period, which is the temperature increasing from the initial temperature to the operation or holding temperature. And in the red part, it's actually the high pressure and the high temperature processing. And afterwards, there will be a cooling session. Let me keep it running. And so you can see the temperature increase and then decrease. Okay, but you might be a little bit confused because in typical case, we need the temperature to be 121 degrees C. And if we don't, how can we heat it up above 100 degrees C? Because water will boil, right? And then in that case, we cannot heat the water up above 121 degrees C. And in this case, and the system looks open, and there's no way that we can pressurize it. So here's the trick actually. If you look at the system here, in the middle, there's a sterilization section, right? And in this section, you can see that the pressure, it's actually sealed by the water, right? And the pressure is added by the water level difference, the level of water difference there. For example, you guys learned about the high school physics that the pressure here is equal to rho GH, right? And then there's a pressure difference, and the pressure here is actually equal to 1 atmosphere plus the pressure provided by this height of the water. So that's why that we can keep the core part, the holding temperature section to be always pressurized, because we are using water as the kind of the ceiling in this case. So this is a very well designed and interesting system, and actually that it's very unique and design. And let me see if they have anything else. Okay, so that was the one that I want to share with you, because it's a very, very interesting design. And this is how we call it hydrostatic retorts. Basically, we use the water to provide the pressure to help the temperature reach more than 121 degrees C. Okay, so is there any questions about this system?
I have a question.
Yes, Christine, go ahead.
Is the overpressure retort,
Mhm.
is that a batch system or a continuous retort?
This is a batch system. But really depends, because in the one that I showed you here, it can also do the overpressure. But in the in conventional case, right now it's hard to say, because conventionally we can only do overpressure retort in batch process. But you know, technology blooms, and people come up with great ideas, and they can do they can achieve overpressure retort in a continuous system. So everything is evolving. It's hard to make a conclusion. And so that's why I won't ask this type of question. Just in the past, the overpressure retort is usually a batch processing, and they use 50 psig, which is greater than the normal pressure here.
Okay, cool. Thank you.
Sure. Okay. So this is the last part of our commercial system. And this one is, you guys saw it in the pasteurization, the UHT and the aseptic processing system, right? And a lot of dairy products, especially soy milk, and like coconut milk, they're using this system. So basically, the idea is that we have two parts, the container and the food. And the container will be these two will be sterilized separately, and we'll sterilize the food in another product line. And finally, we kind of merge these two systems together in an aseptic zone. So in the aseptic zone means it's always sterilized over time, either people using UV light or a lot of different ways to keep it out of any contamination. And anything that is moved into the aseptic zone is also sterilized. So this is a perfect normally packaging area to fill those food products. But we have to make sure everything that we bring into the aseptic zone is contaminant free. So that's the concept of the aseptic processing system. Okay, and to sterilize the food, we have different ways actually. There are two ways. One is called direct heating. So the reason we call it direct heating is because we have the heating medium directly contact with the product. So which means the steam will be mixed with the product. And they have different ways like steam injection, steam infusion. They either by spraying or by in the pipe. So it's very efficient because we have direct mixing, right? Extremely rapid and suitable for heat sensitive foods because it's very fast. But it requires portable steam because we are actually blending the steam into the food, right? And it will also cool it down very often required because we kind of diluted it, okay? And there's not much energy regeneration because we all the heat is dispersed into the food. And the other way, so remember that direct heating, it's direct mixing of the heating medium of the food and the food. And indirect heating, there's something between the heating medium and the food. There's no direct contact, no direct mixing. And we talk, as I talked about before, we use a plate heat exchanger, a lot of the tube exchanger and the scrap surface heat exchanger. Basically, there's something in between it, and it's typically metal because metal has got a heat transfer coefficient. Okay, and this is pretty good for liquid foods, right? Because we cannot push those solid foods through this heat exchangers. The third thing is that we can cool it down quickly using cold water. And so the features of the indirect heating, there's a good regeneration capacity, which means we are recovering the heat by the heat exchange. And also the operation cost is lower, and we have less complex control. We don't have to, because in the direct heating, right? After mixing, we have to evaporate the water by vacuum. Usually we have to evaporate the excessive water, but here we don't have to do it, right? And in the stable, this is more stable as well, and we don't need the steam water to be portable, right? Because they are not mixing. But the issue is that the surface, because the heat exchanger, they are very thin layer of those tubes or plates, and assume that it's overheated somewhere of the milk, then the milk can easily clog those thin area. So that will cause which we call the fouling, and it takes a lot of time to clean it. And that's always the issue with the heat exchangers. So that's the difference between the direct and indirect heat. Okay, so now we talked about all three commercial sterilization systems. The batch process, the batch system, right? We had the steel retort, the rotary retort, and the last one was the overpressure. Overpressure we can do it can be both, right? It can be either batch and continuous. And in continuous, we had the hydrostatic retort, right? Remember, we had the water to control the pressure. And the last one was the aseptic processing. So we had the food and the packaging material, they sterilized separately, and they are kind of merged in the aseptic area, and we do all the packaging and filling. Okay, and the two ways to heat up foods: indirect heating, mixing with the steam, and the direct heating. Use indirect heating using the heat exchanger, and the direct heating using steam mixing. Okay, so I was planning to do a breakout room for this part of like activity, because I have a bunch of different type of food. Want you guys to discuss. Let me see if we have time. It's okay. I think we have time. I will send you to different breakout rooms, and group 1, 2. You guys will talk about discuss about the flavor fresh pouch. What do you use to process it? What type of retort would you use? And group 3 and group 4, you guys will talk about the I haven't divided your groups. Let me see how can I do this. Breakout rooms, create rooms, 10 rooms, and automatically. Okay. So I have created all the rooms, and I'll go through the products. Okay, remember your room and remember the product. Okay, so group 1 and group 2, you guys will do the fresh pouch, and group 3 and group 4, you guys will do the beans and the tomato paste. Okay. Group 5, group 6, you guys will work on the beef stew, okay, and the Irish stew. Group 7 and group 8, you guys will work on the chicken and the chicken broth and the turkey gravy. Group 9, group 10, roasted turkey. If you don't remember, you can always ask me to go back. Okay. So, okay, I think we have everyone back. So group one, group two, what do you think? What retort are we using for the pouch? Okay, so let me ask group one this time. Who wants to share? We have Chloe, Alaya, Emily, and Hector in the group one.
We said that we think it would be overpressure retort because it has a flexible package on it.
Excellent job. Yeah, this one was a very tricky one. You guys got it. So everyone else understood. So because we are in in pouch, it's quite flexible. So when we are using those overpressure processing, the cans, the lid usually cannot tolerate the large pressure difference, and typically we have to use some flexible material, and the pouch is one of the best for the overpressure retort. And great job, group one. Okay. So the second one is the beans and the tomato paste. Which type of retort would you use? Let me ask group 4 to answer this question this time.
We were talking about maybe a rotary retort because they're pretty viscous.
Great. Yes, we have to use a rotary retort for this type of product. We have to manually induce a lot of agitation. Excellent job. And next one is the beef stew and the Irish stew. Group 5 and 6.
Yeah, so we weren't 100% sure on it just
Mhm.
because like it's a very chunky thing, but like the
Yeah.
soup isn't necessarily really viscous.
Mhm.
So, but also just like thinking about the container, it's got like that thin layer of film. So if you heat it up, like would it burst it if there's like steam formation? So maybe the overpressure retort, but then also we're thinking possibly using the rotary retort so that it like agitates it a bit more because it's semi more viscous.
Yes, but you mentioned that the package is not metal, so it might not be tolerating the ultra high temperature, right?
Correct.
So there are a couple ways that we can do it. So as you mentioned that the overpressure retort definitely works because this is quite soft material, and the other one, do you think? So in the aseptic processing, we have two ways, right? One is the direct heating, the other one is indirect heating. The indirect heating requires a heat exchanger, which is usually the liquid. But how about the direct heating? But we have to pump it somehow, right?
Yeah, that makes sense.
That's just my guess. I don't know if they process it using aseptic processing, because I would say overpressure processing definitely works. Aseptic can be a little bit tricky here.
Mm.
Okay, this one is quite difficult. Group 6, what do you think? Alison, Eva, Claire, and Isabella.
Sorry, did you say something? You cut out on my computer.
Oh yes, I mean, mine was also my guess because I didn't check for these two type of products how these two brands process their this type of products. So I want to hear how you guys think about this problem.
I honestly don't really know.
Okay. Yeah, this one could be tricky, and I encourage you guys to check it out. Those stew products with those like chunk meats and potatoes blended in. What is the possible way to sterilize it?
I know we didn't cover it today, but do you think they might employ like a hot fill and then package technique?
Yes, we'll talk about the next class actually. But Chris, you brought a very good suggestion. That's probably the one. Okay. So group 7 and group 8, you guys had the chicken broth and the turkey gravy. Let me ask group 7 first. Casey, Nolly, Patrick, and Reno.
I was thinking you could do like an aseptic process because it is like a really thin liquid that could be pumped. But it also is in like a metal can. So you could do just like a still retort.
Still retort? Nice. I think a still retort definitely works for the chicken broth. And the turkey gravy might be a little bit viscous. What do you think, Patrick?
Yeah, the gravy probably is slightly more viscous, so you might need to do a rotary retort, or you could do aseptic.
Yep. Good job. Group 8, you guys agree?
Yeah, we said pretty much the same thing. I just had a question when it came to like the continuous retort. When would you like use that compared to like still retort? Is it like a money thing or?
Yeah, it's a money thing. It is more capital cost, but less labor and less operation cost. So one time and one time investment, and then maybe long-term benefit. And so it might be better for those large-scale production. Okay, great. And next one, the last one is the roasted turkey, group 9, group 10. Let me ask group 9 first, probably. What do I have? Delaney, Kate, Christine, and Christina.
Yeah, so we thought it was gravy, and so we said like pretty much what the other group said, that yeah, pretty much what the other group said.
Okay. So group 10, what do you guys think? Julia, Michaela, Nicholas, and Sarah?
Our group said overpressure retort because it looks like it's in a glass jar.
Overpressure retort. And also the lid. Do you think this lid is flexible lid? Because you know that overpressure, there's a huge pressure difference inside outside the can, right?
So I guess it would have to be flexible, or?
Yes, usually it's flexible because we apply a large amount of pressure there, right?
Okay, yeah.
So that's why usually we do it for pouch processing. And for glass, it sometimes can be a little bit risky, right?
Oh, I see. So
for pouch processing, would that be
Mhm.
let's see. Oh yeah. So it would still be overpressure retort.
I guess for
This is-
this one, it might be too overpressure. We have to choose a pretty good lid, I guess, so that we can the lid can be a little bit flexible. Since the bottle it looks like a glass bottle. I mean, if it is a plastic bottle, it might be better, right?
Yeah, that makes sense.
Sorry.
Right.
I was gonna say, could you do aseptic processing on it?
Yes, this one is possible. Although it's viscous, but we can still use indirect heating to heat up the gravy, right? Yes, aseptic processing definitely will work here, and also maybe the conventional rotary retort, right? Because it's so viscous. Does it make sense?
Yeah, thanks.
Yes. Okay. So any other questions here? So when we talk about these choices, there's no one like simple like no exclusive answer. As long as you talk about what is the property of the food, and there could be a couple of different choices. Okay. So here's the comparison between the conventional retorting and aseptic retorting. So in stability-wise, they are both very stable. Okay, but nutrition loss actually aseptic processing is a little bit lower because we are using a heat exchanger. Remember that heat exchanger, we heat up everything quickly and cool down everything quickly, right? So I showed you guys a temperature curve in the pasteurization. The temperature only holds at 100 something degrees C for a couple seconds and drop down rapidly. So that's how the heat exchanger can help with the aseptic processing. And we can minimize the nutrition loss in that case. Sensory quality, because of the aseptic processing, we very rigorously control the process time. So sensory-wise, it's usually more feasible. And we also save 30 more percent of energy because we can recover the energy by those, because think about when we have a very hot product and then we want to cool it down, we can use a very cold water to cool it down, and the water can be heated up, and this heated up water, we just need to bring the temperature a little bit higher, and then can be used as a heating media. So in that case, we actually recovering the heat during cooling, and this process helps us to increase the energy efficiency. And the labor-wise, the aseptic processing is lower, right? Because it's more like an automatic filling. Everything is, you guys had a packaging line in the pilot plant. I know many of you have worked there. You see the filling and the packaging, sealing, everything is automatic, right? But for the retort, conventional retort, it requires much more labor. So that's their difference. And I think in terms of food, typically because the aseptic processing requires a heat exchanger process, so we can only process food with very small particles. If we have bigger particles, they have to go to the in-container processing. If we have a large piece of meat, there's no way that we can do aseptic processing. Okay, so that's a recap of the today's class. It's a little bit long class today. So first we learned about the sterilization, what's the difference between commercial sterilization and the conventional sterilization. Basically, conventional one, we have 12D reduction, very strict, but in the commercial sterilization, it's less than 12D. It really depends on the food type, and we can be 8D, 6D, really depends. And we also learned about what is aseptic processing and how that different from the conventional retort. Okay, so conventional retort, everything is the package, the food is packaged and processed and never take out afterwards. But aseptic processing, we sterilize food in the by heat and sterilize container by heat, and then we move them to aseptic region to kind of put them together. Okay, so that's their difference. And we learned about what is cold point and where are they? There are two cases, right? If it's very viscous without any convection, the cold point will be right in the middle, right? There will be the geometry middle. But if we have convection, which means the liquid is moving like water, then the cold point will be slightly below the geometry center. Okay, it's typically 1/3 of the height. And 3 different types of commercial sterilization systems. Batch processing, we had the steel retort and the rotary retort. Okay. And the continuous retort, we learned about the hydrostatic retort. There's a JBT company producing a very nice hydrostatic retort. Basically, they use that water level to control the pressure in the sterilization region. And finally, we had covered the aseptic processing, 2 types of heating. Direct heating is the direct mixing of the heating media and the food. So steam will be mixed with the food directly. Okay, and so the steam has to be portable. And another case is we used a heat exchanger, right? Like tube exchanger and the plate exchanger. So, and finally, you guys did a pretty good job in choosing a good, appropriate retort system for different type of food. Okay, so that's all about this class. Tomorrow we'll have our dehydration lab, and this is a very long lab, and normally it takes 3 hours. It will be very, very challenging tomorrow for us to do 2 groups, but we have to try it out anyway. So I encourage you guys to try your best to read through the handout tonight. It was posted yesterday online. So tomorrow I will talk very minimal to ensure that you guys can start working as soon as possible because the time is really tight. And we'll start with the group 2, 3, and 4. You guys will do pre-treated air drying. Basically, you will cut the apple and peel the apple and use citric acid, ascorbic acid, and sulfite to pre-treat them. And afterwards, we'll air dry them. So it's called a pre-treated air drying. Group 1 will work on direct air drying without any treatment. So it's like a control. And group 5, you guys will come a little bit later because the work is a little bit easier, but you guys have to do a lot of cleaning afterwards. And group 5 will work on the freeze drying. Okay, so basically it's freezed, then it will be dried. So read through the handouts tonight. and we'll have a very busy day tomorrow. And any questions before we finish?
I checked on the Canvas page. I can't seem to find the live handout. I'm not sure if you haven't made it viewable yet.
Sorry, Ethan, I can barely hear you. Can you repeat?
Yeah, I checked on the lab Canvas page, and I can't seem to find the live handout for this week.
Oh, okay. Thanks for reminding me. I think I forgot to activate to make it visible. Okay, I will make it visible as soon as possible. Thank you, Ethan. Any other questions? Do you have any questions about the lab report due this Friday? There are a couple of things, right? It requires you to compare the different products. I mean, it was from the previous year, and I did a very minimal change on it. And I understand that this time you guys didn't have chance to look at the product before processing, and I think you can in those cases, if you can barely compare before and after, the best thing is to do is to guess. I mean, I won't be taking points off and be judging this part, but try to keep other parts like comparing those heating curve, those parts to make sure that those parts are written well. And if you have further questions, I have a office hour on Thursday, and feel free to come.
I actually have a question about the lab notebook.
Yes.
So what do you expect us to put in the lab notebook as for like the data collection?
In this case, I would say the weight before and after. That's the only thing, I think.
Okay. And then for in the lab report itself, do you want us to like copy and paste like the graphs from Excel or just okay?
Yes, copy and paste it.
Okay, thank you.
Any other questions? Okay, great. Thank you guys, and that's it for today. I hope you guys have a good rest tonight, and tomorrow will be a very long day. Okay, see you.
Thank you.
Thank you.
Professor.